In this chapter, we will consider the reaction of free radicals with either alkanes or alkenes. So radicals, they can either react with a sigma bond of the alkane, or they can react with the pi bond of the alkene. Let's consider the first case where free radicals react with alkanes. So you're going to start with an alkane, any type of alkane, and you're going to react it with a halogen. The halogen that we are using here is either a chlorine or a bromine. Normally, we don't use iodine because the reaction will be very slow. We don't use a fluorine because the reaction is going to be too reactive. We know that this is a free radical reaction because of the conditions of the reaction. So you need to have heat, or you need to have light, or you need to have a peroxide, any one of those in there. So here we are starting with an alkane, and the reaction is going to proceed by substituting the hydrogen of the alkane by the halogen. So your product is going to be an alkyl halide and a byproduct. The reaction is going to keep going on as long as you have hydrogens around the carbon to replace. So the reaction can proceed either by a monohalogenation. Here I am using chlorine, so it's going to be monochlorination, meaning that I'm replacing one hydrogen with a chlorine. The reaction keeps going. I can replace now two hydrogens with the chlorine, so I'm going to have a dichlorination product, 3 hydrogens or 4 hydrogens in there. It's going to keep going until it replaces all the hydrogens around the carbon, as long as you stop the reaction. So once you stop the reaction, then you can control the type of product that you need, either mono, di, tri, or tetra halogenation. We said that there are 2 types of halogens that we can use, and the halogens can be either chlorine or bromine. Now, chlorine is very reactive. So with the chlorine, you're going to end up getting more than one product. Chlorine will proceed by reacting with every different hydrogen. Let's go ahead and consider an example. Again, this is a free radical reaction because I am starting with a cycloalkane. There is no leaving a group in here, and I am using light as a condition. So in this case, chlorine, since it's very reactive, it's going to replace every different hydrogens that I have in my structure. So here I do have a tertiary hydrogen. So this one is going to be a tertiary hydrogen. And I have here a primary hydrogen. And I have here a secondary hydrogen. I have another secondary hydrogen over here, which is different than the first secondary hydrogen. And I have a third secondary hydrogen over here that is different from all the others. So see how many different hydrogens I have in there. Chlorine, since it's very reactive, it's going to replace every single hydrogen of those. So I will end up getting, in this case, 5 products. I'm going to end up getting a replacement of the tertiary hydrogen by the chlorine. This is going to be my first one. And then I'm going to end up getting my second product, replacement of the primary with a chlorine. My third, just make sure that the product that you are forming is not duplicated though. So it needs to be a different isomer. So in this case, I will end up getting 5 constitutional isomers. So that is going to be a chlorine in this case. And these are my 5 constitutional isomers as a product from the reaction of the methyl cycloalkane with the chlorine. All of these products in here, they do happen at the same time. However, the most stable product is the product that results from the replacement of the tertiary hydrogen, because this bond over here, the sigma bond, is the weakest bond. So this is going to be the most stable product or the major product. And all the rest are going to be minor products. But again, all of these 5 products, they happen simultaneously and they do happen at the same time. The ratio for these products is not the same though, because the major product is going to form at a higher percentage than the minor product. The only thing here is that all of the products, they do form at the same time. Bromine, on the other end, it is very selective. And with the bromine, you only get one product. That's it. So if I'm using that same example with the bromine, then in this case, and react this with bromine in presence of light, since the bromine it is now selective, it's going to choose the weakest sigma bond and it's going to replace it. And the weakest sigma bond is the bond that belongs to the tertiary carbon. This bond can be easily broken by the bromine. So bromine is going to replace that tertiary hydrogen, and you're going to end up getting your tertiary alkyl bromide. There's the tertiary alkyl bromide in this case. So notice the difference between a bromine reaction and a chlorine reaction. A chlorine reaction is very reactive. So chlorine is going to proceed by replacing every different hydrogen. So you're going to end up getting more than one product depending on the number of hydrogens. And all the products are constitutional isomers with respect to each other. All the products, they do happen at the same time. However, the major one is the one that gets broken by the weakest sigma bond, which is the tertiary hydrogen replacement. On the other hand, with the bromine, you just get one product in there, which is the replacement of the tertiary hydrogen with the bromine. Let's consider the mechanism of the reaction. Since the bromination forms just one product, so we're going to consider the mechanism from the bromine example. The mechanism with the chlorine proceeds exactly the same in there, except you would need to keep repeating the mechanism in there for the different types of products. So the mechanism is going to proceed by 3 different steps. The first step is initiation. This is what starts the reaction. And with initiation, I am forming a free radical. To form a free radical, normally what you do is you take your reagents and you react them with each other. So these are my reagents in there. So you react the reagents with each other. I'm going to take my bromine reagent and I'm going to react it with light, meaning that I'm going to shine some light on the bromine. And what's going to happen is that the light is going to break that sigma bond between the two bromines. The sigma bond normally between two electronegative elements is very weak, and that can be broken easily with light. Of course, the mechanism here is going to be by a homolytic cleavage. So once the sigma bond breaks, every electron goes to one of the bromines. So you're going to end up creating a free radical bromine. So you have a bromine free radical here and a bromine free radical there. Now, bromine free radicals are very reactive. These are intermediates. So the intermediate in this reaction is going to be the free radical. And free radicals are very reactive. And this is what's going to start the reaction. The reaction does not start before forming the free radicals. So you need to form the free radicals and then the reaction is going to start. So these are my reactive free radical that starts the reaction. Not all the bromines are changed into free radicals in the presence of light. Some of the bromines are going to remain unreacted. So we're going to call them unreacted Br2 in there. Okay, here you go. So we're going to end up having free radicals and unreacted bromine. The free radicals are more reactive. These are our intermediate. These are more reactive. So these are going to start the reaction with the cycloalkane. The next step in the reaction is called propagation. And propagation, it's the step where you form your product. So in this step here, I'm going to form the product. In the initiation, you're going to form the reactive, a free radical that is going to start the reaction. This is the difference between both. Propagation is 2 steps. The first step, you take your alkane or cycloalkane, whatever alkane that you are reacting, and you will start the reaction with the free radical that you made in the first initiation step. We agreed that free radicals are more reactive than bromine. So these are the ones that are going to react first. The rule here is that free radicals, they always take hydrogens. Okay, so put this as a rule. So free radicals always take hydrogens in there. With a bromine, because a bromine is selective, a bromine is going to take, so bromine free radical is going to take the most stable hydrogen, which here in this case, it is the tertiary hydrogen. So let's go ahead and label that tertiary hydrogen over here. And that is going to be our only hydrogen that the bromine free radical is going to take. Pay attention that you are doing a homolytic cleavage in this case. So, and this is a homolytic reaction. So you need to indicate the movement of one electron by showing a half head arrow. So always you start your reaction from the bromine radical. So the bromine radical is going to come and break that sigma bond in there. So it's going to take one electron from that sigma bond, and the other electron is going to form on the tertiary carbon. And this is why bromine is very selective, because what you need to form is the most stable radical. This is the rule. So you form the most stable radical. If a bromine comes and takes any of those hydrogens on the cycle and the CH3, those are going to be the less stable free radical. So bromine is selective because the free radical that needs to be formed needs to be the most stable free radical in there. And then I made over here an HBr. This is going to be a byproduct. So HBr here is going to be a byproduct. This is the first step of the propagation. The second step of the propagation, I'm going to take my free radical that I made. Now, don't forget that free radicals are sp2 hybridized carbons, right? So this one over here is an sp2 hybridized carbon. And sp2 hybridization are planar. So if you have a potential chiral center for the free radical, meaning that that free radical has 3 different groups. Here I don't have 3 different groups, but let's say if it has 3 different groups, then you would need to consider stereochemistry in the next step of the propagation. We'll have an example of this as we proceed in there. But here I don't have a chiral center, a potential chiral center, so I'm going to go ahead and proceed with my reaction. So now the second step of the propagation, I'm going to take the unreacted bromine from the first initiation step. So this is going to be the unreacted bromine, and I'm going to react those with the free radical. As I said, this is a planar carbon. So if this is a potential chiral center, meaning that it has 3 different groups, and I am going to introduce the 4th one, you have to consider stereochemistry, meaning that the bromine is going to attack from the top and is going to attack from the bottom. But here I don't have stereochemistry, so I'm just going to go ahead and proceed. Radicals are very reactive. Keep this in mind. So this radical is going to come, grab an electron from the sigma bond. This sigma bond is an easy bond to break because it is between 2 electronegative elements, and the other electron here is going to go towards the bromine. So notice what I did over here. I created my product. So propagation always forms the product. The propagation step always forms my product. So this here is going to be my product. Plus, I'm forming a bromine radical. Now, by forming this bromine free radical in here, as if I went to the first step of the propagation. So the bromine is going to come and react again with another hydrogen, let's say a secondary hydrogen in this case, and replaces that secondary hydrogen. So if you want just the monobromination product, which is the one product in there, you got to stop the reaction. And to stop the reaction, you have to get rid of the free radicals in the solution. So the free radicals in there, you can get rid of them by the third step in the mechanism, which is called termination. So with termination, you take all the free radicals that you are forming in your reaction and you react them with each other so that you can stop the reaction completely. There are reactions that might have a lot of termination steps, so you can only write 3 termination steps in there. Don't write more than 3 termination steps. So let's have an example over here. The first radical that we are forming is the bromine radical, so we can come and react 2 bromines that with each other. And in this case, we're going to end up getting a Br2. So again, the idea is to get rid of all the radicals in the solution. The second possibility is to get your free radical that you formed, and you react it with the bromine free radical. And in this case, I will be adding to the product because this one is going to be similar to the product. So I will be adding to the product. And the third termination step is to react both radicals that you form with each other. So I have a radical here, and I'm reacting it with another radical that I am forming. All what you need to do is just to create a bond between this carbon and this carbon. So these free radicals will come together and will create a new sigma bond. So you're going to end up getting your byproduct in this case. That byproduct is going to happen at a very low percentage, but it's still a byproduct. So this is the sigma bond that I'm creating over here, and this is one of the byproducts in the reaction. The chlorination happens with the same mechanism. So for example, in this one, I only have one type of hydrogen. All of these hydrogens are the same. So the chlorine is going to replace just this hydrogen, and you're going to get the monochlorination product. Reaction is going to proceed by initiation, propagation, and termination. Always the end of the propagation is going to be your product in there, and then you are going to eliminate all the radicals in the solution by reacting them with each other and stopping the reaction. The only difference in the chlorination is the different products that you are forming. So if you want to draw the mechanism of these different products in there, the initiation step and the termination step for chlorination will stay the same, but the difference is in the propagation step. So you have to draw different propagations every time you are replacing a different hydrogen in there. So this one is going to have a different propagation step than this product, than this product, than this product, because you are replacing here the primary hydrogen by the chlorine. Here you're replacing the secondary hydrogen by the chlorine, here the tertiary hydrogen, and so on. So you're going to be creating different radicals as you go. The first and the second step of the propagation is going to proceed exactly the same. So you're going to have your chlorine radical attacking the desired hydrogen that you want to replace in there, creating a free radical. And that free radical will react with unreacted chlorine that is left from the first step of the reaction, which is the initiation. And you will get your product. The bromines, remember that the bromines are selective, so they are going to select the most stable hydrogen and replace it. So this is the tertiary hydrogen, they're going to replace that. This is the most stable hydrogen over here, which is the secondary hydrogen. Bromine is going to replace it. There is no tertiary hydrogen on this carbon. However, the chlorine is going to be reactive. So it's going to replace every different hydrogen in the structure. So you're going to get the different constitutional isomers. Let's consider a bromination example with a stereochemistry. So if I'm starting with this cycloalkane, and I'm reacting it with a bromine in presence of light. Bromine is selective, so it's going to choose the most substituted hydrogen and is going to replace it. This is a tertiary carbon, so it's going to replace the tertiary hydrogen. This is the only tertiary hydrogen in the structure. And I'm going to end up getting my product in this case. Okay. However, my product is a potential chiral center. So let's go ahead and write it for now as a bromine in there, and consider the mechanism of the reaction. So with the initiation, so I'm going to start with the bromine, and bromine reacts with light. The sigma bond is broken, and you're going to form your reactive free radical in there, two of those, plus unreacted bromine. The propagation, and this is how I want you to write the mechanism of the reaction in there. Show clearly the initiation, the two steps of the propagation. So for the two steps of the propagation, I'm going to start with my reactant. And my reactant here is this cycloalkane. I have this hydrogen over here, and I'm reacting this first with the bromine radical. So the bromine radical is going to come and take that most stable hydrogen, which has the weakest sigma bond, and you're going to get your free radical in there. Notice that the free radical that you're going to form is a planar. It's a planar structure, and it is a potential chiral center. This is not a hydrogen. This is a CH3. Okay, so that's free radical in there is a potential chiral center. And the reason why it's a potential chiral center, because it is connected to three different groups in here. And in the second step of the propagation, you're going to introduce the fourth one. So in the second step of the propagation, you take your free radical, which is planar, and now you're going to react it with the bromine. So now the bromine has two possibilities. The bromine can either attack from the top, and you're going to form a free radical in there, or it's going to come and attack from the back. Okay, so that free radical in there is going to react with the bromine, and you're going to form the second stereoisomer. So you have two possibilities in this case, and you have to consider the possibilities whenever you have a potential chiral center. Always remember that free radicals are planar, and planar intermediates will have the reagents attacking from both sides. So in this case, you will end up getting the following in there. I'm going to keep the long carbon chain in plane. If the bromine attacks from the top, then the CH3 is going to be at the back. I'm just going to leave the CH3 over here because this one is not a chiral center, okay? But this is a chiral center in there. Plus, my second possible product, if the bromine attacks from the back, then the CH3 is going to be pushed to the front. So these are my two possible products in there, and these products are considered to be enantiomers. So these are the two products that I am forming. So it's more accurate to represent the products in a form of stereochemistry pair of enantiomers rather than being general like this with representation of your product, especially whenever you have a chiral center. Plus, of course, my bromine free radical in there. So I need to stop now the reaction. So you go to termination. Now with termination, you don't have to consider stereochemistry. Just go ahead and react all the free radicals as we did before. So these free radicals, please use the half-head arrow. This is called, after all, the mechanism of the reaction. And then use your free radical in there that is formed and react it with the bromine radical. This is going to add to the product. You don't have to show stereochemistry at all in there. So this is going to be the bromine. And then the last step of the termination, or the last reaction, there are more reactions in there because you're generating more free radicals, but we are just going to consider these three reactions in there. So this free radical is going to come and react with another free radical of the same kind in there. I like to place the free radicals next to each other like this so that I would know that I want to make a bond between these two carbons. It's easier to view that. So here you go. I'm going to end up forming a bond. So this is the bond that I'm going to make. Here you go. And I have my cycle. And on my cycle, I have a CH3. So this is going to be my byproduct. This is another example over here, but now with the chlorine. And because you are using chlorine, you're going to end up getting more than one product because you have different types of hydrogens. And the chlorine is reactive. So you're going to end up replacing the secondary hydrogen here, the tertiary hydrogen here, and the primary hydrogen in here. Now, when you replace each one of these hydrogens, they are going to go by their own radical. So replacing the primary hydrogen would result with a primary radical. The primary radical is not a potential chiral center. Here is not a potential chiral center. The tertiary radical is also not a potential chiral center. But on the other end, replacing that secondary hydrogen will be a potential chiral center because you have three different groups in this case. So that is going to be your planar free radical. And then the chlorine from the second step of the propagation will have the options to attack either from the top or from the bottom. You need to change the stereochemistry of the CH3. So if chlorine attacks from the top, the CH3 can either be at the top or it can be at the bottom. And if chlorine attacks from the bottom, then the CH3 can assume both positions. So for this reaction, I got a total of 1, 2, plus 4. This is 6 different products.